So let's do this statistical factor model in the data. And just to show you how easy it is, I have here my, I use MATLAB. There's my MATLAB code for producing it. I make the covariance matrix of yields. I take the eigenvalue decomposition. QL is eig of sigma. And then we just look at the columns of Q. And that tells us our factor model. So here are the columns of Q. Disp Q shows us the columns of Q. Let's look at the rightmost one. In MATLAB, the largest eigenvalue with a 5.80 standard deviation is plotted on the right. And the loadings are 0.46 points. They're almost all the same. Now, what does that tell us? That tells us, first, this is how you create the factor from the data. In other words, you about evenly weight all the bonds to create the factor. Second, it's a set of loadings. When that factor moves, each bond moves. The short-term bonds move by 0.6. The long-term bonds move by 0.3. Well, how shall we name that factor? A factor that when it moves, pretty much all bonds move by the same amount. Level. What that's telling us is that with a 5.8% standard deviation, a lot of the variance of bond returns can be described by this level factor. Let's look at the next one. Next column of Q are uncorrelated. The factor is uncorrelated. The column of Q tells us how to form the factor. Well, that's an HML factor, right? You form the factor by plus 0.5 of the long-term bond, plus 0.36 of the 4-year bond, minus 0.74 of the 1-year bond. You're forming the factor as an HML-style portfolio. It also tells us if the factor moves, where do bonds go? Well, if the factor moves by 1 unit, long-term bonds go up by 5, short-term bonds go down 0.74. That makes a slope movement in the yield curve. And I labeled the next one curvature the same way. A picture may make this clearer. All I've done next is plot the columns of Q. There they are in the loadings. Level is the blue one. It moves everybody up or down by the same amount. With a 5.6 standard deviation, that's the biggest movement in yields. Slope is the green one. And you can see this is the weights. That's how you form the factor. And that's how each bond moves when that factor moves. Boom, slope. The level, slope, and curvature comes from the data. It doesn't come from the method. Curvature is the next one. It sends the 2 and 3 up and the 1, 4, 5, and down. And the others, well, the others are kind of idiosyncratic noise zigzag. So you look at this. There's economic interpretation in the first 3 factors, and the other ones are kind of ugh. And then you look at the variances. Level is 5.8, slope's 0.58, curve is 0.10, and the other one are tiny. So you've got 3 huge factors accounting for like 99% R-squareds. Why don't we summarize bond prices by the first 2 or first 3 factors and treat the others as if they're measurement errors, noise, idiosyncratic, and so forth? Now, those, of course, might be tiny pricing disparities that a hedge fund could make a fortune on. But sort of these are attractive as the economically significant, and those as either the errors or the small deviations from the model. How well does that work? Well, to do that, I just plotted the original yields in red, and in blue, the factor model. So here's what happens if we keep only the level factor. There's the original yields. You can see the level factor. The level factor goes up and down. You multiply it by about the same number for each bond, and you get about the same prediction. It's capturing the level movement of the yield curve, but it's not capturing at all the spread movement. We need another factor for sure. That's not a good enough factor model. How about level plus slope in the next graph? Well, now we're making progress. Red is the actual data. Blue is the fit from the factor model. When I throw away the final factors, I only keep the level and slope factor. And you can see now we're capturing both the fact that yields went down and also that yields spread out. But we're still missing a little bit. There's still a last couple of basis points between model and data there. How about we take level, slope, and curvature and leave out those little zigzaggy idiosyncratics? Yes, there are both red and blue lines on this plot. You can sort of see it really carefully in 2002 that they're a little bit different. But the 3-factor model fits this data almost perfectly. And the other most important thing is that the 3 factors have an economic pattern to them, whereas the others seem to be idiosyncratic pricing movements. So that's how a three-factor model fits to term structure data, the statistical model. Just for fun, I did the same thing for the Fama and French. So we had Fama and French's 25 portfolios that we looked at previously. The Fama and French factor model, we said, that is pretty much a factor model. It's like an APT. The R-squareds were 90%. What happens if we eigenvalue decompose the 25 by 25 Fama-French covariance matrix? This is just eigenvalue decompose covariance matrix, plot the columns of Q. The first factor, what shall we call that? Well, that's the tendency of all of these 25 portfolios to move together. That's a level. It's the equally weighted market portfolio. What's the second factor? Well, the second factor, you can see, it moves size and book to market in one dimension, and the third one moves size and book to market in the other dimension. The second and third factors together comprise size and book to market loadings. When those things move, size and book to market move. They're about the same variance, so the eigenvalue decomposition doesn't find a size and book to market. It finds two different linear combinations of size and book to market. And just for fun, what's the fourth factor? The fourth factor really pushes on the small growth portfolio and the large value portfolios, which interestingly were our big alpha portfolios. And the Fama-French model works beautifully if you use these factors as the pricing factors as well. So that's armed with the eigenvalue, you can easily become a 2-year-old with a hammer to which everything looks like a nail. But it is a very simple way of characterizing the factor structure in many different kinds of securities.